Good morning. Today we're going to be working with arcs and chords of a circle. So there's some specific properties that chords have in circles, and we're going to investigate those this week with our arcs. All right, so Chapter 10 or Unit 10, Classwork 7, Arcs and Chords of a Circle. We're going to go do some prior knowledge first, and then we're going to dive into some of these properties. So in each of the following, find the value of x. Well, what do we know about A, B, and C? What kind of triangles are those? Because the sides are congruent, those triangles are isosceles. In isosceles triangles, recall the sides are the same length and the base angles are the same length. So in A, x would have to equal 42 degrees. In B, we're going to look at that vertex angle of 30 degrees, 180, take away 30 is 150. And 150 divided by 2, each x would have to equal 75 degrees. And same idea, if one base angle is 40, the other base angle is 40, that makes 80, which means x has to equal 100 degrees. Also in prior knowledge, and this is when we did our polygon unit, we've got an isosceles triangle, and we've got this whole vertex angle up here that measures 38 degrees. And so what do we do when we have an isosceles triangle? That's right, we cut it in half. Half of 38 is 19 degrees. Our 22 is here, and we're looking for our altitude and our base, and then we're going to double the base to find the base of the isosceles triangle. So that's right, SOHCAHTOA. Cosine 19 degrees is A, oops, oh, that doesn't look good. A over 22, which means A is going to be 20.8. Sine, the opposite over the hypotenuse, is B over 22, which means B is going to equal 7.2. So we got to go back and see what the question's actually asking. We want to know GJ, well that's A, the altitude, 20.8 inches. HJ, that's B, 7.2 inches. And FH, well that's B times 2, 14.4. Here we go, today's new learning, chords of a circle. Now, I'm not drawing chords right now, I'm going to be drawing in radii. Draw line segments OA and OC. What kind of triangle is OAC? Well, we know it's isosceles. And we know that because the radii are the same length. All right, properties of chords. In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Well, we're going to say the arcs are congruent. I'll use that scratching on the wall. All right, if arc AB is congruent to CD, I'm going to put two ticks here. Boom, boom, and boom, boom. If those two arcs are congruent, then we're going to say that, can we prove that segment AB is congruent to CD? Well, let's go ahead and draw in our radii. If in doubt with these circles, draw in your radii. Well, we know all the radii have the same length. What can we say about angle APB? I'm going to do those in a different color. Angle A, these two angles. Well, I'm going to say that those angles are congruent. I'm going to say they're congruent because they're central angles and their arcs are the same, which means those central angles must be the same. So I'm going to say congruent central angle because the arcs are congruent. And what triangle could we prove that those two, what triangle shortcut could we use to prove that the two triangles that you see are congruent? Well, to me, it looks like side angle side. And because the triangles are congruent, would not AB and CD be congruent by CPCTC? Corresponding parts of congruent triangles are congruent. If the triangles are congruent, then any corresponding parts that we didn't use previously must be congruent too. So that's the first one. If the arcs are the same, the arc segments are the same. If the arc segments are the same, the arcs are the same. Here we go. Given the diagram to the right, AD is congruent to DC. The segments are congruent. Arc AD is congruent to arc DC. So the measure of AD must be equal to the measure of DC. So if AD equals 2x and DC equals 40, then we can just set those equal. So 2x equals x plus 40, which means x is 40 degrees. Next property. And a circle. If a radius or a diameter is perpendicular to a chord, then it bisects that chord and it bisects that arc. So we've got AB perpendicular to CD in circle P. Can we prove that CP is congruent to DP, and can we prove that arc CB is congruent to DB? And here we go, a beautiful proof. The radius OB is perpendicular to the chord CD in circle P because that's given. So angle OPC is congruent to OPD, which also equals 90 degrees. So we're talking here, here, and here. Because isn't that what the definition of perpendicular actually is? OC is congruent to OD, because those are radii. And all radii in a circle are congruent. OP is congruent to OP because that's the reflexive property. So the triangle OPC and OPD are congruent. We've got a right angle we've got our hypotenuse congruent and we've got a corresponding congruent side. So we're going to call this hypotenuse leg, which means that CP must be congruent to DP by CP DTC. So we proved this first part. Now, can we prove CB is congruent to DB? Well, in order to prove that those arcs are congruent, we need central angles to be congruent. And is it true now that we know these two angles up here are also congruent by CPCTC? And if those angles are congruent, then their intercepted arcs must also be congruent, because congruent arcs have congruent central angles. So our example, P has a radius of 13 feet. 13 here, 13 here. Chord AD is 24, so we can already now know that we can break that in half. So we've got 12 here and 12 here. We know we've got right angles, and if we have a right angle, we've got right triangles. I'm going to redraw POD. POD looks like it's like so we know this is 12, we know this is 13, and using Pythagorean theorem, the square root of 13 squared minus 12 squared, OP is 5 feet. OB is the perpendicular bisector of AD, which means that AB and BD, the little arcs, are the same. So we want to find AB if AD is 268. This isn't a well-written problem. When we say AD, we're talking here. And that is 268. So 360 degrees minus 268. That's 92. And we cut that in half. So 92 by 2 is 46. And so AB is 46 degrees. And the last property we're learning today, in the same circle, if two chords are congruent, only if they are equidistant from the center. So in circle E, we've got these radii. Boom, 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 boom. We already know those triangles are congruent. We know those triangles are congruent by hypotenuse leg. And so if the triangles are congruent, then EF must be congruent to EG. So what we're saying in reverse is if EF is congruent to EG, then the triangles are congruent. So, this up. Oh, Word's not responding. We'll give it half a second. There we go. All right. So given the diagram to the right, if PQ is 12.5, then this whole length must be 25. Well, since the distance from the radius to the chord is the same, SR must also equal 25. We're going to practice. Let's look at these real quick. The distance from the radius to the chord is the same, which means the chords are the same. X equals 15. We've got a perpendicular bisector. X must equal 7. We've got vertical pairs. Those vertical pairs are central angles. If the central angles are congruent, the arcs are the same. Distance from the center to the chord is the same. If one of the segments is 7, the whole chord is 14, which means x equals 14. And if the chords are the same, the distance from the radius must be the same, which means x must equal 8. And x must equal